Welcome back to the Foundry by Forge College. If you caught our previous explainer on synthesizing PO effects on network efficiency, you'll know we spent quite a bit of time unpacking proof of history's magical clock. But today, we are diving into our component integration overview. Because, honestly, a perfectly synchronized clock is pretty useless if the rest of the network doesn't know how to set its watch by it, right? We're going to see how Solana's components actually sync up in the real world to keep everything moving at that famous lightning speed. Here's our blueprint for today. We'll start with the network's grand timetable, explore the rail network metaphor, track a transaction's epic journey, establish setting integration contracts, discuss keeping the trains running, and finally, wrapping up our journey.
Let's kick things off with Section 1, the network's grand timetable.
So, let's get right into the engineering blueprint. Component integration is literally the way proof of history, timestamping, leader scheduling, transaction propagation, and account storage all interlock. It's that crucial bridge converting an abstract time signal into totally predictable system behavior. Think of POH as a master conductor. If you don't have this tight integration, you're not getting a symphony. You're just getting a bunch of instruments playing their own random tunes, which, let's be honest, just causes a massive headache.
And why is this so critical? Because even small mismatches between components lead to measurable variance in latency and data durability. Without this tight integration, mismatched buffering policies just create absolute chaos. Imagine this massive, oversized rail yard, where instead of reliably delivering cargo, your data just kind of wanders off to take a nap. If the components don't absolutely agree on the exact sequence of events, your latency is going to spike and throughput drops to zero. Coordinated integration is what eliminates that variance.
Moving on to Section 2, the rail network metaphor.
To really visualize this, let's compare this abstract architecture to a physical rail network. Proof of history? That's our timetable. Validators are the stations, transaction propagation is the actual train service, and storage is the rail yard where the cars finally park. Now imagine sending 1,000 train cars to a station that has absolutely no platforms. Complete disaster, right? Well, that's exactly what happens if our propagation train ignores the POH timetable. Everyone across the network has to consult the exact same schedule. And this brilliantly illustrates the trade-offs we constantly have to make across three critical axes. First, timing fidelity. Second, delivery semantics, like best effort versus exactly once. And third, storage acknowledgement. High timing fidelity means you need way more buffering space at the stations, while demanding exactly once delivery shifts all the heavy lifting over to the rail yard storage logic. It's this massive constant balancing act between face-melting speed and enforcing rigorous safety checks so your assets don't just get lost in transit.
All right, Section 3, a transaction's epic journey.
Our train is departing. Let's follow a batch of 1,000 transactions through 4 key steps during a high concurrency window. Step 1. The leader assembles the block and tags the transactions with their POH sticks. Step 2. It streams them through the best effort propagation layer, which is our incredibly fast, but sometimes slightly unpredictable train service. Step 3. Validators catch these cars, validate them, and carefully buffer them by their exact POH tick. And Step 4. They are safely committed to persistent storage. It's basically a beautifully orchestrated relay race where every single handoff absolutely matters for the overall speed.
Now, I really want you to focus on this validator buffer policy. The rule here is to accept out-of-order deliveries, but immediately key them by their POH tick. If the train service runs late or the cars arrive totally jumbled up, this crucial buffering policy acts like a waiting room. It keeps all those transactions perfectly organized by their POH tick until the full contiguous sequence arrives. This neatly converts the absolute chaos of network propagation into strict local ordering guarantees, completely avoiding disastrous rollbacks. That brings us to Section 4, setting integration contracts. Making these explicit, small handoffs observable totally shifts how complexity moves around the network. We're looking at 4 main contracts here. The leader provides a signed header. Propagation promises best effort delivery. The validator maintains a tick-keyed buffer. And storage dictates the durability policy. The trick is, if you tighten one, like, say, demanding absolute perfect delivery, you suddenly require massive amounts of network bandwidth. It's a deliberate, ongoing game of operational whack-a-mole. Take storage, for example. You have synchronous versus asynchronous storage acknowledgement. Synchronous gives you much stronger guarantees. We know for a fact the data is safe, but it comes with higher latency. You're basically making the train sit and wait at the station until all the paperwork is meticulously filed. Asynchronous lowers that latency, letting the train zoom right through, but it implies a much higher restart recovery effort if something goes wrong. It's a very practical choice. Do you keep the trains running incredibly fast, or do you optimize for how painful it will be to clean up if a train actually derails?
Now for Section 5, keeping the trains running.
So here is your practical integration checklist. You need to define your ordering expectations, choose delivery semantics, define storage acknowledgement levels, specify buffer and eviction policies, consistently monitor contract adherence, and, this is absolutely crucial, run fault injection tests. This step-by-step checklist takes our abstract system goals and turns them into concrete, testable actions. It ensures that under massive pressure, every single node makes the exact same deterministic choice. That completely avoids a split-brain scenario where half the network thinks one thing happened and the other half strongly disagrees. The absolute most vital point here is establishing binary tests. For example, a strict rule. Validators must not apply transactions with POACH ticks older than the last committed tick. By turning this kind of philosophical goal into a simple true or false test, we guarantee strict tick monotonicity. If a transaction fails this test, it's instantly rejected. It acts as a ruthless but highly effective bouncer to maintain global network order.
Finally, Section 6, wrapping up our journey. Let's do a quick recap. Component integration relies entirely on small, highly testable contracts that constantly reference those PO ticks. Our rail network model does a really good job of visualizing the real-world operational trade-offs we have to make between speed and safety. And using simple, clear monitoring metrics helps us detect any integration fractures super early. By treating proof of history as the ultimate canonical ordering anchor, we can successfully turn the totally abstract property of time into operational, rock-solid predictability. But here's a question to leave you with. Now that our contracts are firmly set, what concrete infrastructure coordination patterns can actually implement these flawlessly at a massive global scale? I want you to think deeply about that as you prepare for our next lesson. To dive further into these engineering challenges and really master Web3 architecture, be sure to visit forge.college. Thanks so much for hanging out with me on this explainer, and I'll catch you in the next one.